Our next reaction for aromatic rings is the nitration reaction. So the nitration reaction will allow us to take an aromatic ring in the presence of nitric acid and sulfuric acid and some heat and forming nitrobenzene. Now the nitro group, as we'll see, is not necessarily the most useful group by itself, but as we'll learn later on, you can fairly easily turn the nitro group into an amine, and at that point it's available for a large number of other reactions that we can use. Now, in this reaction, as well as our last one, the sulfonylation, we're going to see some slightly unusual mechanistic steps. And we're going to see that right here in the electrophile generation for nitration. So as we said, we have a combination of nitric acid and sulfuric acid, both good acids. So we're going to actually see nitric acid play the very, very unusual role here of functioning as a base. And the oxygen in nitric acid will actually remove a proton from sulfuric acid. That gives us a leaving group with this oxygen can now add its electrons in and kick out water. So now we've generated our electrophile for the nitration reaction, NO2+. This NO2+ can be attacked by our aromatic ring. Forming our sigma complex. Which then, with water present, can function as a base, remove the hydrogen, and form nitrobenzene. Now we're going to see here next that this nitration reaction, its mechanism is extremely similar to our final aromatic substitution reaction, the sulfonylation. Now the sulfonylation is basically the nitration reaction minus the nitric acid. So sulfuric acid and heat to form this product. So now if you recall in the first step of nitration, the nitric acid removed a proton from sulfuric acid. Well, obviously we can't do that here since we don't have any nitric acid, but we could have a highly similar reaction between two molecules of sulfuric acid. And that's what happens is we transfer a proton from one sulfuric acid to another. And if you recall with the nitration, that gave us an intermediate that could kick out water to give us a good electrophile. Same thing here. Remove the proton, electrons shift over, we kick out water, and we get our electrophile SO3. From here, this reaction is going to look very similar to what we've seen. The aromatic ring will attack SO3. That forms our sigma complex. Again, water can function as our base, remove the hydrogen, we regain aromaticity. And then we just need some sort of acid, which obviously with sulfuric acid is one of our reagents. We have plenty of acid present. And we protonate and form our product. So of our 5 electrophilic aromatic substitution reactions, this one is probably the least important and the least useful. But traditionally, this reaction did have some very important uses to it. And the most important use was to make a class of compounds known as sulfadrugs. Now, sulfadrugs are not as widely used as they once were, because while sulfadrugs have the advantage of being very cheap and usually very easy to make, they also have the disadvantage of very high allergy rates among medications. Now, you'll also notice that in all of these reactions that we've done, none of the aromatic rings that we started with had any substituents on them. And so in our next video, we'll start talking about, what if we try and do one of these reactions and there's already a substituent there? How does that affect where the next reaction takes place?